Welcome everyone, this is Alba. Today we explore NaiveBayes, one of the simplest and fastest models for text classification. We will start from the motivation, build the intuition step by step, and understand how the model makes predictions. In this lecture, we begin with text classification as a motivating problem. We compare discriminative and generative approaches. Then we derive the NaiveBayes assumption, learn how to estimate probabilities from data, and finally apply Bayes' theorem for prediction. Many tasks in machine learning involve text. For example, classifying emails as spam or non-spam, detecting topics such as medicine or graphics, or understanding sentiment in movie reviews. Because text is not numeric, we need a way to convert documents into meaningful numerical features. To work with text, our first step is to convert words into numbers. The simplest method is the bag of words model. We take all unique words in the dataset, and for each document we record whether each word appears or not. This gives us a very simple yet powerful numeric representation. In the bag of words model, each document becomes a vector. Every entry in the vector is 0 or 1, depending on whether a specific word appears. This turns textual documents into interpretable numerical data that algorithms can work with. Let's see a small example. With a vocabulary of 6 words, the sentence "Roger Federer is fast" becomes a vector marking which words appear. This highlights how the bag of words representation captures presence or absence of specific terms. Here we compare two sentences. Although they differ, they both contain the word is. Shared and distinct words like these help the model understand similarities and differences between documents. If we stack the sentence vectors as rows, we form a matrix. Each column corresponds to a word, and each row represents a document. This matrix is the starting point for models such as logistic regression or NaiveBayes. So far, we have focused on representation. We can now convert any document into a numerical vector. The next question is, how do we use these vectors to decide the class of a new document? For that, we need a probabilistic model. With the bag of words, each document becomes a long vector of zeros and ones. How do we determine whether it belongs to sports or politics? We can approach this in two ways, by learning a boundary between the classes or by understanding how each class generates its words. This leads us to generative models. Different types of articles use different vocabulary. Sports articles often mention players and matches, whereas political articles include words like law or election. If we can estimate how likely each class is to produce certain words, we can apply Bayes' rule to classify new documents. This is exactly what NaiveBayes does. There are two main perspectives in classification. Discriminative models directly learn how X maps to Y. Generative models, on the other hand, learn how each class produces its data and then use Bayes' rule to choose the most likely class. Both approaches aim to predict the correct label, but they do so in different ways. Here we compare discriminative and generative models. Discriminative models learn the probability of the label given the input, written as P of Y given X. They focus on drawing a boundary between classes. Logistic regression is one example. The objective is to maximize the conditional likelihood. In other words, they try to directly separate the classes as well as possible. On the other hand, generative models take a different approach. They learn how each class actually generates its data. This means they estimate both P of X given Y and the prior P of Y. Then they apply Bayes' rule to compute P of Y given X. Their objective is to maximize the joint likelihood of the data and the labels together. So the key difference is discriminative models learn boundaries, while generative models learn the underlying data generation process for each class. Bayes' theorem connects three components: the likelihood, the prior, and the evidence. For prediction, we want the class with the highest posterior probability. Because the denominator is the same for all classes, we only compare the numerator. To apply Bayes' rule, we need the probability of the document given the class. But with thousands of words, modeling all combinations directly is impossible. NaiveBayes makes a key assumption. All words are independent given the class. This simplifies the computation dramatically. If the word offer appears more often in spam than in legitimate emails, it becomes a useful signal. NaiveBayes uses these word-based probabilities to estimate how likely a document belongs to each class. With a large vocabulary, the number of possible word combinations becomes enormous. It's impossible to estimate all combinations from data. The independence assumption reduces complexity from exponential to linear in the number of words. Because many word combinations never appear in the dataset, attempting to learn the full joint distribution would lead to many zero probabilities. Assuming independence avoids this issue and allows the model to work with limited data. Although the independence assumption is not realistic, NaiveBayes works well because it only needs approximate word statistics. Strong indicator words dominate the probability and guide the classification effectively. To classify a new document, we compute how likely each class is to generate its words. We compare these class scores and choose the class with the highest probability. This makes the method simple, fast, and intuitive. Training NaiveBayes is extremely simple. We count how many documents belong to each class to estimate the priors. Then, for each word and each class, we estimate how often the word appears. We apply smoothing to avoid zero probabilities. During prediction, we multiply the word probabilities for each class and multiply by the class prior. The class with the highest resulting value is our prediction. This computation is efficient and works well even for very large vocabularies. Here we restate Bayes' theorem in its complete form. The posterior combines what we believe before seeing the data and how well the data fits the class. This formula is the core of NaiveBayes. The numerator captures two things: how common the class is and how well it explains the document. The denominator normalizes the result, but because it is the same for all classes, we skip it in practice. The medical test example shows how a rare event can dramatically affect the posterior probability, even with a highly accurate test. This illustrates how priors influence predictions. In this text example, seeing the word win strongly increases the likelihood of spam. By multiplying the prior and the likelihood, NaiveBayes chooses the class with the largest score. In this example, two words, win and offer, appear together. Even with the independence assumption, combining these probabilities leads to a very strong preference for the spam class. NaiveBayes is not one single model. It is a family of models that all follow the same probability rule. The key difference comes from how each variant treats the feature values. In our case, with bag of words, each feature is binary. A word either appears in the document or it does not. This matches the Bernoulli distribution, which describes events that can only be 0 or 1. Because of this, Bernoulli NaiveBayes is the most appropriate model for binary text features. For comparison, multinomial NaiveBayes handles word counts, and Gaussian NaiveBayes is used for continuous numerical data.